So some of you might already be familiar with some of the ideas in this video, especially if you're taking Stat 230 or have some previous exposure to probability and statistics. But I think there's still value in going through this video so that we're all on the same page as far as how we think about these ideas in Methyl 131 and what are the important aspects to focus on in this course. Right. And so we want to collect data about random variables, right? And so you will for sure be getting a more formalized treatment in Stat 230, but generally speaking, you can think of a random variable as a variable that can take on one of multiple potential values or outcomes, right? And we currently don't know which one. And so we're kind of trying to anticipate the future in some sense. And so random variables could describe, for example, the amount of a loss, right? Currently, maybe unknown, but there are many, many possibilities in the future. Or, whether a loss might occur in the future or, how many losses might occur. And so, again, in this course, we're usually talking about pure risks with just potential future losses. And so, what are the kinds of things that we want to know so that at the end of the day, we can characterize or describe these random variables? One is the likelihood or frequency component. Basically, how often does the loss occur? Does the outcome occur? Right. So, for example, how often have we observed earthquakes to occur? That's going to give us some data that can inform us in terms of modeling the probabilities of future earthquakes occurring, right? How likely. We also want to know the severity, the value or the severity. If it were to occur, what are the possible outcomes? What are the possible values in this case, right? Loss of life, loss of property, they're all different kinds of values. We also want to know aspects associated with hazards at the end of the day, not necessarily just because these are areas where we have some control, but from a quantification perspective, these are things that are going to affect the underlying probabilities of the different outcomes, and then the actual values of the different outcomes themselves, right? The sort of frequency or severity component. And so where can we turn to find data? Obviously, ideally, if we had our own historical data to work with, right? This is much easier if you're a large company that has just, operated for a really long time, historically observed, many observations. For example, Amazon can observe all of the car crashes from their self-driving vehicles, for example. If the organization doesn't have data, there could also be industry history as well, industry benchmarks that might be available. And then if there is just, very limited data, this might be the case for example, earthquakes or other climate-related natural catastrophes that simply don't occur frequently enough for us to actually, to use as far as developing a probability distribution only based on the data. These are cases where we can then turn to theoretical models as well, maybe combining, climate science models in addition to the observed data. And so at the end of the day, basically, we want to combine all of this information together to develop a picture about the random variable. And so by picture, what I mean by is basically organizing the data to build a probability distribution. And so there are a couple of components here to a probability distribution. You can basically think of probability in this course as a sort of rate of frequency of occurrence of some particular outcome relative to all possible outcomes. So some kind of proportion or sort of relative frequency of occurrence. And so to develop a probability distribution, then we first want to just identify all of the possible outcomes in a given situation, in a given scenario. And so I want to distinguish this a bit from, not just all of the observed outcomes, but all of the possible outcomes. For example, right, as a small business, you can't just not worry about theft just because the firm has never experienced theft before, right? Or you can't just ignore liability because you haven't been sued in the past. We really want to identify the set of all possible outcomes in a given situation, whether or not, they've actually occurred historically. And so A couple of terms here that, again, you would have heard in Stat 230. We want these set of outcomes to be collectively exhaustive in the sense that together they are complete. They account for all possible outcomes. And then we also want them to be mutually exclusive, which basically means that each outcome in our set doesn't overlap with any other outcome. Right? So for example, if we're talking about loss amounts as our outcome, we can't at the same time, we can't simultaneously have a $500 loss and a $1,000 loss at the same time, right? And so mutually exclusive. One outcome basically means that no other outcome can be realized as far as identifying all of the possible outcomes. And then once we've identified all of the possible outcomes, we then want to calculate probabilities for each of these outcomes. And so together, that's what characterizes a probability distribution to describe some kind of random variable. And so here's an example of a simple sort of a loss history data set where in the first column, we basically have the outcome of interest, which is the severity or the amount of a loss. For example, $0, $200, $1,000, so on and so forth. And we also have the number of observations or the frequencies with which we observe every single outcome. And so using then this loss history data, we would be able to develop a probability distribution across all of our potential outcomes based on what we observed. And so again, thinking of a probability as the relative frequency of one particular outcome compared to all of the outcomes, right? And so in this example then, if we have 2,000 observations in total, and we're interested in the probability based on our observed data, the probability of an outcome of $0 of losses, then our proportion, right, of observations equal to this outcome of 0, 1,200 divided by the total number of observations, right, the sort of relative frequency. And so that's going to be 0.6. And this is also not uncommon in insurance loss data for most of the most likely outcome to be 0. And then the probability then, based on our observed data, of a $200 loss, right, would be what we observed, the number of observations we observe equal to 200 divided by the total number of observations that we've observed. And so this is going to be 0.25. Right, for the outcome 1,000, right, 200 observations of 1,000 divided by 2,000 observations in total, we have 0.1, right, and then completing the other two, 0.04, 0.01, right, and so I want to mention that we can do a quick check that this is a probability distribution we've developed where the sum of all the probabilities is equal to 1. Right, that's that collectively exhaustive component where we've characterized all of the outcomes and mutually exclusive. Right, we cannot have two outcomes be realized at the same time. And so as far as characteristics of these probability distributions, we can think of both discrete and continuous random variables. These are our two main types of random variables that we tend to encounter. And so a discrete random variable is basically a situation where the outcomes that the random variable could take on are only going to be integer values. For example, right, 0, 1, 2, 3, 4, 5. Right, countable integer values. And so these kinds of random variables might oftentimes be used to describe frequency, right, count distributions, the number of counts. And so, for example, along the x-axis then, on the left side, we'd be looking at integer valued count outcomes potentially, and then the height of each of these bars would be associated with the relative frequencies of observing each of these integer outcomes. On the flip side, we also have continuous distributions, and these are going to be random variables where the outcomes themselves take on a continuum of possible values, right? So not just 0, 1, 2, 3, could be 0.25, could be 1,000 point whatever, could be, 3.14159, for example. But basically the possible outcomes are continuous. And so oftentimes this is going to be used to model severity distributions for the amount of a loss. And so in the continuous case, we have the density here on the right plotted as a smooth line. So you can think of a similar interpretation in this case, as in the possible set of outcomes are along the horizontal axis. And then here, the majority of the time, the values, the outcomes are going to be in the middle. And so this is an example of a symmetric distribution here on the right. As far as the continuous distribution goes. I did want to briefly mention, though, that as far as insurance losses goes, typically speaking, they tend to be right skewed, commonly skewed distributions where most of the time they're very small, right? But there are also infrequent, there are large, rare values as well. And so there are many ways to summarize an entire probability distribution with a single value. And so first we're going to talk about some of these measures of central tendency. So this is basically our best estimate of what's going to happen, right? The tendency, the central part of the distribution, the kind of middle outcome in some sense. And so for example, right, one is the average or the mean or the expected value. And so in this case, we have X bar is what we use to denote the sample mean. And so we calculate the mean as the sum over all possible outcomes, right? Over all possible outcomes, the sum of the ith outcome weighted by the probability of that outcome. And so this is basically a weighted sum of all possible outcomes where the weights are the probabilities of each outcome. And so, for example, if we go back to the previous example, right, in this case, if we're talking about the sample mean, we are going to be taking a weighted sum of all possible outcomes weighted by their individual probabilities. And so the first outcome is 0, weighted by the probability of it occurring is 0.6, plus the next outcome, 200, weighted by the probability of it occurring, right, so on and so forth, 5,000, 0.04, and then lastly we have 10,000 weighted by its probability, right? And so altogether, this is going to be equal to $450 is our expected outcome, right? And so if we look at our complete set of outcomes, at least as far as this example goes, right? If we look at our complete set of outcomes, the mean is not equal to any individual outcome necessarily. It's not one of the possible outcomes here, but the idea is that over time, right, with many, many repetitions, the average, the expected value of the outcome is 450 in this case. We can also think about the median, which is the value in the middle of the distribution. So basically half the time we're below the median, half the time we're above the median. And so going back to our previous example, we can see that the outcome 0 has a 60% chance of occurring, right? 60% of the observations are equal to 0. And so that means 0 is that middle outcome for this distribution. And we can also talk about modes, which are essentially the outcome that is most common, right? What we most frequently observe. And so in the previous example, that would also have been 0. And so I also wanted to mention that a given distribution might have multiple modes as well, right? So this might be a unimodal distribution, but we can also have, for example, bimodal distributions, multiple potential, more frequently observed outcomes. And so whereas central tendency is our best estimate of what's going to happen, we can also think about measures of dispersion. Basically, how far away are values from the middle, from the average value? Basically, how spread out is the distribution? And so one example is the range, which, we basically take the largest observation, subtract the smallest observation, and that makes it kind of susceptible to outliers that are observed, which is why we tend not to use it. We can also then talk about the variance. Essentially, how far away is each observation away from the mean on average? Basically, what is the average sort of squared difference from the mean? And then the variance is itself then, because of the squared in terms of units, is going to be in units squared. And so we can also think about, from an interpretability standpoint, the standard deviation taking the square root of the variance, which is also, the average spread of the values around the mean, but is expressed in the same unit as the original measurement. And so going back to our previous example then, in this case, based on our observed data, our range would be just the largest subtract the smallest. And so in this case, right, 10,000 subtract 0, which is 10,000. Our variance, right, basically taking the sum over all of the outcomes, the squared difference of the outcome from the mean to and then weighted by each of the probabilities. And so recall the mean, or the average, was 450. And so we're basically going to take every single outcome. So for the first one, 0, subtract the mean, squared, weighted by the probability of that outcome occurring, 0.6. And then for the second outcome, which is 200, right, take the outcome, the difference, the distance from the mean, squared, weighted by the probability of that outcome, plus we have $1,000 outcome, subtract the mean squared, weighted by the probability of it occurring, right? I'm going to skip to the last term, right? Our 10,000, subtract the mean squared, weighted by the probability of it occurring. And so in this case, we're going to get 1,907,161. And technically speaking, the units are in dollars squared, right? Less interpretable. And so we can consider the standard deviation, which is just the square root of the variance. And so we would end up with 1,381 in this example, right? So is this high or low? This, compared to the mean, at least, right? This is kind of 3 times the size of the mean, right? And so is this large? I mean, basically scale matters, right? Because if the mean were instead 100,000 instead of 450, then, a standard deviation of just 1,300 might not be as large, right? But kind of keeping that in mind, right? Standard deviation is a measure of variability, but at the end of the day, we still have to consider the scale or the magnitude. That leads right into the coefficient of variation, which, essentially when the expected value differs across distributions we're comparing, we can't simply compare the standard deviation to find out which one is riskier, relatively speaking, right? For example, if you have a distribution with a mean of 4 and a standard deviation of 3, versus a distribution with a mean of 4,000 and a standard deviation of 3, right? Those are very different as far as, relative risk goes. And so basically the scale or the magnitude does matter. And so the standard deviation, for example, right, it takes into account the mean in and of itself, right? The average difference from the mean in some sense. And so the magnitude of the mean also matters. And so the coefficient of variation then is needed when we're comparing relative risk when there are different means, right? And so this is basically important when we're making decisions that also affect the mean. Obviously, if you were comparing 2 distributions that had an identical mean, then it is sufficient to just compare the standard deviation. But in general, as far as a measurement of relative risk goes, that's what the coefficient of variation is describing. Another one that's common in actuarial and financial risks, especially if we're interested in extreme outcomes, is the value at risk, or the VAR. And so this is not what is the largest loss possible in our probability distribution, but rather what is the largest loss that's probable? What is the maximum probable loss? And so the idea is that the decision maker is going to choose a probability level that is quite high, usually something like, say, 99%. Then the value at risk, or the maximum probable loss, is basically the amount such that at least 99% of the time, losses will be below this level, right? Equivalently, we can think of, at most 1% of the time, losses will exceed this level. And so this then, using the maximum probable loss as the value, the amount of losses that are probable to occur based on whatever level you've chosen. And so this level might be chosen based on the risk tolerance then of an organization, for example. At what point do I decide that a loss has a sufficiently small chance of occurring that I'm going to ignore the values above it as far as risk management decisions? And so, for example, if you were to increase your level from 99% to 99.9%, right, then you're basically using a higher threshold. The value at risk would go up. You're using a higher threshold in your decision making, such that now 99.9% of the losses are going to be below this level. And so if you're more concerned about the tail risk of the extreme outcomes, then using a higher value in your decision making would make it so that you're willing to spend more money to manage this risk, right? You're more risk averse. And so at the end of the day, recognizing that if you had to make risk management decisions based on the maximum possible loss, that might not necessarily be the most efficient use of your resources, right? And so if based on your risk tolerance, if you're going to say, okay, instead I'm going to use the 99% value at risk as the maximum probable loss, most of the time, losses will be below this level, and we make our risk management decisions based on this level instead, then basically based on our risk tolerance, thinking about the kinds of resources that we want to put into managing risk versus managing expenses.